Hi friends, welcome to our channel. Let's look at problem 3535, unit conversion 2. Actually, there's a problem that is 3528, this is the unit conversion 1. Actually, this problem here is an extension of the previous problem 3528. Actually, part of the code here will address the problem 3528. So this is the one comment. So here, in order to do this problem, you need to know some concept, that is modulo multiplicative inverse. So this modulo inverse of a number a, modulo m, is a number x such that if x times its a equals 1 in the sense of modulo m. Typically, we require that this a and m, so is the largest common divisor is 1, right? So here, for example, if you want to compute the multiplicative reverse of 3 modulo 7, so you can this because it's very simple, right? You can do some simple algebra. You can try, right? 1, 2, 3, 4, 5. So you can see 5 is the modulo multiplicative inverse of 3 modulo 7. So this number is 5, right? So in Python, you can compute this by this one. So if you want to compute the modulo reverse of a modulo m, you can see put here a, put the exponent to be -1, and then this is the m. So with that said, we are going to do the coding. Actually, I'm not going to read through the problem statement because it's rather straightforward to digest that, right? So here, the main point is that we need to return this according to the requirement of the problem. So with this concept here, you should be able to do it easily. So here, the number of nodes is bounded above by 10 to the power 5. This is a large number, so we need to take time complexity into consideration, right? So here are some consistency assumptions, right? So it's guaranteed that unit 0 can be uniquely converted into any other unit through a combination of forward or backward conversions, right? So actually in this problem, so we are given n nodes and n-1 edges. So actually it forms a tree data structure, right? This graph we are going to work with actually is a tree. So with that said, I guess we provide enough backgrounds. Now let's look at the coding. So we are going to put it into two steps. Step 1 is some preparation. I guess for the preparation, it will address this problem actually, right? So then we just step 2 is prepare the return, right? So here, in order to do this operations, first let's get number of nodes. So it's going to be the length of this conversions plus 1, right? So then we have a constant that is 10 to the power 9 plus 7. So notice that this is a big prime number, right? So you can check it, or you can use prime decomposition to check this is indeed a prime number. So with that said, let me first build the graph. So the graph I'm going to use collections default and dict. So I'm going to use set as the container, right? So then for u, v, and the conversion factors, so in conversions, so I'm going to do this. So graph and u add, because this is the set, v and f. So it means that each unit represented by u equals cf times v unit of the unit represented by v, right? So this is the here, right? A single unit of type source is equivalent to this number of units of type target, right? So this actually is the graph. So what we want to do? So we want to initialize this one times n. So we want to get the relation of from the source or the unit 0 is here, right? Unit 0. So the unit 0. So and the relation of unit with the unit 0, right? So here each unit I, represented by I, and with unit 0, right? So for this, we can do DFS, or BFS. So here, let me first do BFS in an iterative format, and then I'm going to also provide you a DFS solution. So here, I'm going to write a hyperfunction. So from the source is going to be 0 because this assumption, right? So we're going to start from here. Actually, this is a directed graph, right? So we don't need to use a set, so to avoid repetitions. So here, collection stack. So here, what I'm going to store will be the source and the standard unit. So I'm going to use unit 0 as 1, right? And then we're going to do traversal valq. So we get the node and we get the corresponding value now. So this q pop left, right? And then we're going to set from root and this node. So equals the value. It means 1 unit of the unit 0 equals this amount of unit at this node. And then we're going to check the neighbors. So for neighbor and conversion factor in graph node. So we're going to do append operation. So we're going to append the neighbor. And also we need to do the modulation, right? The value times the current conversion factor, but don't forget to modulo this number. So this is the hyperfunction. If we do BFS from 0, so this function is going to modify this from root variable. So notice that why we can do this, because from root, this is the list. List is mutable, right? So therefore, in other words, we don't need this non-local from root line. But you can do this, but that's redundant. So once we have this, let me maybe do a print, right? The print from root. So after we call this function, so we can run it. Yeah, you will get this one, right? So now let me prepare the return. So for this purpose, let me initialize a result variable. So the result variable will be first 0 times the length of queries. So what shall we do? So basically for I, U, V, right? In enumerate. So this enumerate includes this I. And then we have queries, right? So queries in terms of length 2 arrays. So we have this. Then so the result I, so corresponding to this node. So it will be something like this. So we do the reverse, multiplicative reverse. That's the from root u. Then -1, the modulo, right? This is the prime number. Notice that. So here from root v, right? And then you do modulo overall. So this is from this return requirement, right? So after you do this, so you just need to return the result variable. So this will form a full solution. Yeah, it passes the 2 test cases. So now let's look at the generic case. Yeah, it passes the generic case. So here, actually, let me make some comments. The first comment is that here I pop from left. So if I pop from right, so you pop from left corresponds to because you are using it as a queue. So this will be BFS. But if you pop just from the right, it's going to be you pop from the right and also you append, that is also from right. This will be a stack behavior. So this function, though we write BFS, will be a DFS solution. Let me run it. The same. Let me Yeah, so if you want to use DFS, you can also just use a plain list and without using deck. That will be sufficient. So, but here, let me recover that. I'm using pop left. So the reason is that I want to give you another one. So this is the BFS solution, right? So let me also write a DFS solution. So still I'm going to modify this variable, right? So DFS. So as I commented, you can choose this to be pop just to make it in fact a DFS one. But here for DFS, I also want to provide you a recursive solution. So here for you, let's see, for V and conversion factor in graph source. So what we do is from root, so we can V equals say from root source times the conversion factor. Let's just also modulate this one. And then what do we do? So we do DFS V, right? So this will be a recursive one. So you can call this function, and then this will modify this list. So let's check it. Yeah, it passes the 2 test cases. Now let's look at the generic case. Yeah, the same thing, right? So personally, if you want to write some short code, so this way of doing recursion in terms of DFS might be preferred. However, if you want to understand details, so I would say this iterative format might be the preferred one. So this is the comment on DFS and the BFS. So I also encouraged you to look at problem 3528, right? So essentially here, up to here, after you call DFS, then you can return this list. This will be solving problem 3528. So with that said, I guess that's it for the current problem. So here I want to mention that this is the 1000th YouTube video in our YouTube channel. So actually in that YouTube channel, there are a lot of playlists. You are welcome to check out the problems there and using the playlist to do some practice. With that said, thank you for watching.